Hey AP Chem students, how you doing? This is Coach Scott. We're going to be talking about the subatomic particles, all right, that makes up the atom. So we talked about in class that electrons have a much smaller mass than a proton or a neutron, like 4,000 times smaller. So when we talk about the mass of an atom in atomic mass units, otherwise known as U, we generally consider that to be the sum of the protons and neutrons in the atom. So the number of protons plus the number of neutrons equal the atomic mass A in atomic mass units. So Rutherford postulated that there was a very small dense nucleus and that it contained protons, and he didn't really know about neutrons yet. And the electrons are around the outside of the atom, and most of the atom is empty space, not air, just space, right, or nothing. So if the nucleus was 10 to the minus fourth angstroms, it's another term for like the size they use, then the actual atom or the element would be 1 to 5 angstroms in diameter. All right, so the nucleus is much smaller than the atom itself. So here's some new terms for you. The number of protons in a nucleus is what we call the atomic number. Remember, the number of protons is what makes the element or the atom what it is. Okay, so if you have 1 proton, you're always going to have hydrogen. If you have 92 protons, you're going to have uranium. And that's where you find it on the periodic table. Now we designate the atomic number as Z. So the atomic number or the Z number is always at the top of the symbol on the periodic table. Okay. Now the mass, okay, are really the nucleons. And what we mean by nucleons is the subatomic particles that are in the nucleus. So you got protons and neutrons are in the nucleus. Therefore, they are the nucleons. So when someone talks about a nucleon, you're talking about a proton or a neutron. So we have another designation we use for the mass number or the number of protons and neutrons. Okay, it's A. Now to get the number of neutrons, if we subtract A or the mass number, or really subtract Z, the atomic number, from the mass number A, we get the number of neutrons, because Z, the atomic number, is the number of protons. A is the number of protons and neutrons. Oop, wrong button. So there's a couple of ways we indicate the mass of a particular atom. One is we call it X minus A, the first method. Another one is we use the nuclear symbol method. The A, which is the atomic mass number, is on top, and on bottom is the Z number or the atomic number. Okay, when we say silver 107, okay, that means that atom is silver. Okay, and whatever the number of protons that the atomic number for silver is, that's the number of protons. 107 is the mass number of that particular atom, okay, in our sample. 47 is the number for silver. So if we were going to write it like this, we'd have the mass number on top, the symbol, Ag, and the A number, or the Z number rather, the atomic number on bottom. So let's think about this. How many electrons does this element have? So this is a neutral element, right? It's not charged. Okay, so the number of electrons is equal to the number of protons. So that would be 11. That has 11 electrons. So how many protons are present in an atom with a mass of 13 AMU if it has 7 neutrons? So the mass number, the A, was 13. There's 7 neutrons. To get the A or the Z number, okay, 13 minus 6, there would be 6. So that would be A. So what we're talking about is atoms of the same element. Atoms of the same element can have different numbers of neutrons. So carbon always has 6 protons. It's atomic number 6. So its Z number is 6. Some carbon atoms have 6 neutrons. So its A number would be 12. Some carbon atoms have 8 neutrons. So its A number would be 14, or the number of neutrons plus the number of protons. Okay? So atoms always of the same element that have differing number of neutrons are called isotopes. Isotopes. Now, isotopes of an element always have the same number of protons, but they will differ, but the differing masses are due to the differing numbers of neutrons. All right? So this is carbon-12. It's got 6 protons, 6 neutrons. Okay, and the number of protons, electrons equal the number of protons. Carbon-14, another isotope, okay, because it has a different number of neutrons, has 6 protons, 8 neutrons, 6 plus 8 equal 14, and of course the number of electrons is always the number of protons. So, let's think about this. What would be the complete symbol for neon 20? Okay, it's got 10 protons, 10 electrons. So on top here, okay, I don't have my little pen, so I'll do the best I can. All right, so there I'm going to have 20 for the A number, 10 for the Z number. Okay, on this one, the Z number is going to be the same, 10, because there's always the same number of protons in neon. It's always going to be 10. The only thing differs on this is the number of nucleons. So here I've got 10 protons, 11 neutrons, so the A number would be 21. This one would be 22 because it's got 10 protons. Let's see if I can make a 2 there. 22. I did pretty good. I'm proud of myself. Okay. Oops, sorry. So an atom that is an isotope of potassium, okay, must have, okay, if I look up potassium, okay, I believe it has 19 protons because the atomic number is 19, and that's what it is. It's C. What species is an isotope of 39 chlorine? Well, it's got to be the same element, so it has to be C, 36 chlorine, or chlorine 36. Notice it's charged, so it's going to have the same number of protons, but the electrons will differ from the protons because it does have a charge. We'll talk about that later. So, not all isotopes are found in the same abundances in nature. Neon 20 is found 90.48% in nature as neon 20. Neon 21 is 0.27%. Neon 22 is 9.25%. So what does that mean? That means in a sample of 10,000 atoms, 9,048 are neon 20. Only 27 out of 10,000 are neon 21. Only 925 are neon 22. Makes sense. So, we talked about the A number, all right? The A number, which is the mass of that one atom, okay? But usually we're not talking about just one atom. We're talking about a sample of atoms, right? So we don't report the A number most of the time. We're reporting the average mass, right? The average of a sample. Okay, so the atomic mass we see on the periodic table is the average atomic mass of all the isotopes of a given element. Okay, so the mass number indicates the exact relative mass of a particular isotope with that element. Okay, that's what the A, or the mass number. So this is the average atomic mass. It's not the mass of one single atom, the 20.18. So how do we calculate that? So to calculate it, we're going to take a weighted average. So we did this last year, but how do we do that? We've got a sample of neon. We know what the percentages are of neon 20, neon 21, and neon 22. So what we're going to do is multiply the A number of each isotope by its percent abundances. All right, and we're going to do this. There's a couple ways to do this, but we're going to go ahead and divide by 100 on the percentages. So if we take 20, which is the A number for neon 20, we know that it's 90.48%. If we go ahead and divide that by 100, and we get 9.9048. Neon 21 we know is 0.27% found in nature. Divide by 100 and we get 0.0027. 22 is 9.25%. Divide that by 100, the percentage, and we get 0.0925. Multiply that by 22. So what we're doing is we're taking a weighted average. Okay, we add these up, we sum them, right? We add the products together. And if you calculate this, you're going to get 20.18 AMU. So let's think about this. Carbon has two isotopes that are stable, C12 and C13. Carbon-14 is radioactive, so it's not very stable. So if 98.89% of all carbon in the sample or in a sample are carbon-12, what's the atomic mass of carbon, or the average atomic mass? We're just going to pop the answer over. So first, to get the number of carbon-13, if we subtract 100, or 98.89 from 100 for 100%, we get 1.10. 1.10. I'm going to go ahead and correct this too. I can. So then 12, or carbon-12, times 0.9889, okay, plus 13 times 0.011. If you sum these together, you're going to get 12.01 AMU. Guess what's on the periodic table? 12.01. So if we're going to do oxygen, in nature, 99.76% of oxygen, 16, okay, is oxygen 16. 0.04% is oxygen 17. Okay, so let's see, 0.2% of oxygen is oxygen 18. Let's hope they calculate this. If you do this question, you're going to come up with 16.00 AMU. And we'll work this in class tomorrow. We'll work this in class too. Calculate the atomic mass of copper. There's two isotopes of copper. 69.1% has a mass of 62.9 AMU. The rest has a mass of 64.93 AMU. So if you subtract 69.1 from 100, all right, you will get the percentage of the 64.93 AMU. We'll do this in class. So, elephants are hunted for the ivory in their task. What do we even worry about isotopes? So game wardens use isotopes to track where the elephants are going so they can help protect them. So, if an element eats a plant from a wet climate, the ratio of nitrogen 15 to nitrogen 14 in their hair will be lower than is typically found in nature. Okay? If they graze plants grown in a dry climate, they will have a higher ratio of nitrogen 15 to nitrogen 14 than normal. Where would you look for an elephant that had a hair sample with a ratio of 0.0045 nitrogen 15 to nitrogen 14, where the normal ratio is 0.034 nitrogen 15 to nitrogen 14. All right, so nitrogen 15, okay, to 14 would be lower if it's in a wet climate. All right, the normal ratio is 0.034 nitrogen 15 to nitrogen 14. So there is a higher ratio of nitrogen 15 than nitrogen 14, right? So that's probably in a dry climate. Drier climate. So that's just one of the ways. Again, they'd analyze the hair for the elephant. So unknown elements and compounds can be identified using a mass spec, a mass spectrometer. A mass spectrometer is an instrument designed to determine the relative mass and abundance of charged ions of a particular substance. So in our discussion of average atomic mass, we have used only whole numbers to represent masses of isotopes. All right. However, because of various reasons, the actual measured value of the mass of each isotope is close to, but not exactly a whole number. Okay. Once we start working directly with data from instrumentation, okay, we're going to use decimal figures and not the whole number to determine the average atomic mass. There's precision of how we measure stuff. So, we talked about this last year. So this is how a mass spec works, and it's a very common instrument that is used in research a bunch. If you major in chemistry, if you take a lot of chemistry classes, if you go into medicine, okay, you will be using a mass spec. So, how does it work? First of all, you shoot the sample into this ionizing furnace, right? So you shoot it in, all right, and it becomes a charged ion. Then it's moved over in a gaseous phase, and it's accelerated through a magnet. So lighter ions are deflected more, all right, are pulled toward the negative part of the magnet. Okay, heavier ions are deflected less, and they're pulled, but because they're heavier, they don't move as quick. Okay, then it goes into a collector or a detection device, right? Then it will determine on the mass to charge ratio of what the mass is, right? So this is the mass to charge ratio. So this would be a 45, this would be a 44, the middle would be a 45, and the 46 is going to deflect less. And then if we know what the sample we started with, and we know the 3 samples we ended with, we can get a percentage of that sample of actually what went through the mass spec. So for a given sample, a mass spec will be produced showing the intensity of signal or the abundance, okay, or the percentage abundance will be in the y-axis. And the relative mass of the ion will be on the x-axis. All right, so this is a sample of neon. Okay, so A, okay, is right around, well, it'd be about right there, okay? That's the mass is around 19.9%. The intensity is 100. So this would be A. This would be A. Peak B is around 22, and that's about, I don't know, that's about 10.2%, or the intensity is about 10.2. Peak C, which would be right there, is around 20.99. Its intensity is 0.29. So we've got 3 peaks here, okay, and these represent the 3 isotopes of neon. Now they're not the same intensity because of the different natural abundance of each isotope. Again, we talked about neon earlier. Neon 20 is got much more than the neon 22. All right, it's around 9%. neon 21 is much less, around 0.29%, or a little less. Now, to get the percentages, if we mass up this intensity, 100 plus 10.22 plus 0.29, we get our total, right? So this was the mass, the max 100. So the total of those three peaks is 110.51. If we divide 100, which was the intensity of the neon 20, okay, or neon 19.99, neon 20, we get 90.5%. If we divide 10.22, which again was the intensity of neon 21 or 22, we get around 9.25%. And again, if we get neon 21 or 20.99, if we divide 0.29 by 110.51, the total of those intensities, we get 0.25. Now, there's software now that will actually do that for you. So to get the average atomic mass, okay, with this sample that we just shot through a mass spec, okay, we can take our numbers that we just used, 90.5%, and we multiply 19.99 times 0.905 or 90.5%, and we sum that with 21.99, 0.0925, plus 20.99 times 0.0025, we get out to 20.18, which is, guess what? That's the mass you see on the periodic table. So what this is the average of the stable isotopes of an element. So we'll work this tomorrow, because this could very easily be a test on the AP test. So I've got an element with two peaks. All right, this has an intensity of peak A is 10.01 AMU. Its intensity is 24.8. Peak B is 11.01 AMU. Its intensity is 100. So if we were to take 100 and add it to 24.8, we get 124.8. Now, like we did before, take 100, divide it by 124.8, that gets us the percentage of 11.01. Okay. Now, this we can pretty well guess. We can look at our periodic table. Pretty sure that's not neon. Could be boron, could be beryllium, can't be sodium, because, yeah, it just can't be. So it's going to be beryllium or it's going to be boron. Okay. Could very easily be a test question. In order to be an isotope of boron, an atom must have a, well, we have to see what the number of protons that boron has on the periodic table. We'll do this tomorrow in class. We'll do this again tomorrow in class. And we'll do this in class. And that's all we want to talk about today, guys. I'll make another video on PES. We went over this last year, and most of you got that. So we'll see you guys this week. We're going to have a great week. We'll be doing mostly problems. Please watch this video. Thanks, guys. Coach Scott out.